Hi, welcome to this lesson on Euclidean geometry, the Pythagorean theorem. So let's have a look at what the Pythagorean theorem is and the proof for it. So if triangle ABC is a right-angled triangle with side lengths AB, AC, and BC, where BC is the hypotenuse of the right-angled triangle, then we have the relationship that AB squared, so this length squared, plus AC squared equals the hypotenuse BC squared. Okay, so let's go ahead and prove the Pythagorean theorem in a rigorous way using this right-angled triangle. So as with any theorem, we start off with the green part, the hypothesis. We construct all the necessary constructions that the hypothesis claims, and then we go ahead and show that the conclusion is true. Okay, so let triangle ABC be a right-angled triangle with these side lengths, and BC is the hypotenuse. So that means that angle A is the 90 degrees. Next, we're going to make a construction. The construction is to create a perpendicular line from the vertex point A down to the point D, where D lies on the hypotenuse BC, but that line is perpendicular to the line BC, so it creates a right angle here. Okay, so you can sort of see three triangles. Okay, you have the larger right angled triangle, ABC. Then inside that, you've got two smaller right angled triangles, ADC and ADB. Okay, so let's go have a look at the relationship between these three right angled triangles. So what we're going to show is that triangle ABD, triangle CBA, and triangle CAD in that exact order are all similar to each other. Okay, so the similarity properties will allow us to use proportionalities of the side lengths, and then from that we're going to deduce the relationship that we are all familiar with, AB squared plus AC squared equals BC squared. Okay, so I've taken the triangles and I've put them like that, and we want to show that they are similar. So we want to show that this angle A1 here, this angle C here, and this angle C here are equal, okay, because then that'll show these first angles are equal. Then we want to show that angle B here in this triangle, angle B here in that triangle, and angle A here in that triangle are all equal. And that'll show that angles are all equal. And then lastly, we want to show that angle D, angle A, and angle D and all those triangles are equal. Also, so far the last one here is straightforward because these are all 90 degrees. So that's fine. So if we can just show one of these relationships, either those three first angles are equal or these second angles here in each of the triangles are equal. If we can show one of those two, then we're done, because by the last one, it'll be angles in triangle as the result, and then all triangles will be similar. So let's go ahead and see how we're going to do that. So notice that in triangle CAD, so this blue one here, we have that angle C plus angle A2 equals 90 degrees. So angle C and angle A2, those added together give you 90, and that makes sense because 90 plus the right angle gives you 180. So that's by angles of triangle, okay? We also know that angle A1 and angle A2 equals 90 degrees, okay? Because this is angle A1 and that's angle A2. So in this larger triangle ABC, the sum of those two angles is 90 degrees. So looking at these first two here, we can deduce the following. Both are equal to 90 degrees, okay? So I have A1 plus A2 equals C plus A2. So I can subtract angle A2 from both sides, and I'm left with angle A1 equals angle C. So this angle A1 here, which is this angle in this orange triangle, is equal to angle C. All right, that would essentially show that these angles here, all three angles here, because these are common angles, right? And those two common angles are equal to angle A1. So therefore, we've shown this angle A equals angle C equals angle C here, okay? And then similarly, we can also show that if you look at triangle ABD, the orange one here, that angle A1 plus angle B is 90 degrees, again by sum of angles in triangle. And then again, using the fact that A1 plus A2 is 90 degrees, we can equate them again, just like we did on the top here, and then subtract angle A1 from both sides and show that angle A2 is equal to B. So this angle A2 here is equal to angle B here, which is equal to this angle, which is a common angle here. Okay, so in all cases, we've shown that the corresponding angles as shown in that order are equal to each other. So by angle, 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 we've shown that all these angles in that exact sequence are equal to each other. Okay, so therefore, we have that similarity coming out by angle, angle, angle. Okay, so now that we've shown that those triangles are similar, we can use the similarity properties of proportion as follows. So these two triangles being similar means that I can take AB divided by BC, right, is the same thing as BD divided by BA, or AB. Okay, so in that exact sequence that we've taken it. All right, so doing that, we can cross multiply both sides by AB and you'll get AB all squared. And then cross multiplying here, we're going to get BD times BC. Okay. Next, if we look at these two triangles being similar, we can see that if I take the relationship AC, right, over BC, then it's the same thing as saying DC over AC. So exactly in the sequence that you take on the left, you take that exact same sequence on the right when you compare the proportions. Okay, so then I can cross multiply again. AC times AC is AC squared, and DC times BC is DC times BC. Okay, so now I'm going to add AB squared plus AC squared. Okay, so AB squared is this side length here, and AC squared is that side length there. Okay, but then that's going to equal to AC squared is DC times BC, and then AB all squared is equal to BD times BC. Now there's a common factor of BC on the right hand side here, so I can take that out, and I'm left with DC plus BD. But what is BC? Sorry, not BC. What is BD plus DC? BD is this length here, and then DC is this length here. But altogether, if I add that up, that's just BC. So I have BC times BC, which is BC squared. So we've proven that AB, this side length squared, plus AC, this line squared, so the adjacent sides of the right angle, or squaring them, adding them together gives you the hypotenuse squared. And that is the Pythagorean theorem. Okay? The converse of the statement of the Pythagorean theorem is also true. So the Pythagorean theorem is an if and only if statement. So the converse, so the backwards direction, says the following. If you know the square of one side of a triangle ABC, say BC, in this case the hypotenuse, is equal to the sum of the squares on the other two sides, the adjacent sides next to the 90 degree, then the angle included between the two sides is in fact a right angle. Okay, so basically the forward and backwards direction of the Pythagorean says as follows. If you know that AB squared plus AC squared equals BC squared, then you know that the angle A, the angle between those two adjacent sides, is 90 degrees. And conversely, if you know that the angle between, if you know the triangle is a right angle triangle, then this formula here, this relationship, will always hold true. Okay, so that is the Pythagorean theorem. We're going to go ahead and do some practice problems. I'll see you in the next one.